Okay, so this is starting a new topic in this course, which is stochastic pattern formation. But now we're going to do it in time, and then next week we'll do it in space. And so the time case, we're just going to look at a system which is spatially homogeneous, and we're going to look at the age-old problem, nearly 100, well, actually now literally 100 years old, probably this year, of population cycles. And I'm going to show you that the standard textbook description of that, which you'll read in any differential equations book or so on, is completely wrong. And I'm going to show you how we actually solve the problem correctly using a stochastic field theory. So what I'm going to do today is going to be using stochastic processes, but I won't need to do formal quantum field theory because it's spatially uniform, so there's only one point in space. The next week, when we look at pattern formation in space and in time, or time and in space, then the description I'm going to give you today will need to be applied at every single point in space and be coupled together, and that would be absolutely horrific. And the way we get around that problem is to use the methods from quantum field theory and Martin-Singer-Rose and things like this. So what I want to do is I want to show you the traditional description of population cycles in predator-prey systems. So I'm going to show you the mean field theory of that. I'm going to show you that the mean field theory doesn't work. And then I'm going to show you how it is that ecologists sort of make a kludge in order to give the answer that they want. But that answer is not correct, and in fact makes predictions that disagree with observations. And then I'm going to show you that we solve this problem by looking at systems at a different level of description. So one of the themes of this course has always been look at the right level of description. And sometimes you actually have to go to a lower level of description than you would expect. And this is one of those situations. And the underlying reason for this is amazingly deep. It's related to the remarks I made last time about stochastic integration and the difference between Stratonovich and Ito stochastic integrals. And in fact, it's related to what are known in quantum field theory as anomalies. And so I will talk about that, but I'm not going to talk about anomalies per se, because actually that work, we still haven't written our paper on it. So that's what we're going to be able to do today. All right, so let me get started. So I'm going to do this lecture. We're going to be more detailed than we were last time. So last time I was just showing you very quickly about Cahn-Hilliard equation and phase separation. Now I want to actually show you why population cycles occur. So the question we're going to be asking is why do population cycles occur? And we're going to answer that by showing you that we can make an ordinary differential equation description. And you're going to see that gives you cycles. And so you're going to think, well, that's great. Now we've understood the problem, but in fact we haven't. I'm going to show you that those cycles are not what you want. They are what are called centers. And so we're going to talk about center versus limit cycles. And then after that, we're going to talk about the failure of the system, or this description. So let's get started. So I wanted to start off by giving you some basic intuition about predator-prey dynamics. So the idea here is understand what's actually happening, and then try to model it using mathematics, and then we'll see how this goes off the rails. So here's the system. So I'm going to think of a box, and now in this box I have two species of creatures. So say the white ones, and then ones in I don't know, red or whatever this color is. Okay, these blobs, those are the prey, and I'll call those B. And then the white ones, those represent predators, and I'll call them typically A. And so what is the basic physics? So here is the basic idea. But here's what happens. I got a bunch of predators, let's call them wolves. And I've got a bunch of prey, let's call them sheep. So they're all in this field, and the sheep are happily munching away on the grass, and the wolves come in, and they see the sheep. So what happens is that the wolves start eating the prey, the sheep, and so the prey population will go down. But the predator population will go up because they get all this food from eating all the sheep. So then they use that energy to make baby predators, and so the predator population goes up. Now the predator population has gone up, but now of course the prey, their population has gone down. So what's going to happen is eventually the predators are going to run out of food, so their population is going to start going down as well. Once the predator population has gone down, then there aren't too many wolves around, and the sheep, which are busy eating the grass and making their own sheep babies, what's happening then is that then the sheep population will start to go up because the predator population has declined. And so once the sheep population goes up, then the predators now have more food to eat, and so they are able to then eat more food, and so their population goes up, and the whole cycle continues. So we can write the idea as step one is that prey eat food, then their population goes up. Therefore, the predators have more food. So the predator population goes up. Then the prey population declines. They've all been eaten. And then the predators, then their population down. And then because of that, then the prey population will go up. So this is the sort of cartoon of the processes that are happening as time proceeds like so. So that's the basic dynamics, and so you can see just by arguing verbally that there are going to be population cycles, and so the question is, how do we model this mathematically? So let's write down the differential equation. So A is the predators and B are the prey. We're going to be thinking of these things as densities. So A is predator. You can think of these as being a number, but really it's density. So I want to think I'm going to call it density, and this is the prey number, or really density. So the difference between number and density is very important because the number is an integer and the density is a real number. So the cardinality of this description matters. So number is an integer and density is a real number. And so this distinction is actually important. So what we're going to do is actually focus then on this description in terms of density, and our main tool for modeling is to use the law of mass action. So let me say what I mean by that. So if I want to write an equation for how dA by dt changes in time, well, that's going to be something like this. If the predators are going to, the only way that they increase in time is to eat prey. So obviously it's going to be the density, the rate at which it increases is going to be proportional to the density of predators, but also to the density of prey. So we're going to write down a term that looks like this, and there's going to be a rate at which the predators meet the prey, and so it's going to be P times AB. But of course, the predators can also just die from old age, so there's going to be a term like that. And if I think about the prey, so what happens to them? Well, they are eating the food, so their population is growing exponentially with some birth rate B, but they get eaten. They don't get to live to old age and die. They just get eaten by the predators, and so their equation of motion is simply given like that. So that's basically a very simple law of mass action, and of course we understand that this is really a spatially extended process, but we're just ignoring space. So this is a mean field theory. And now we can ask, well, what are the steady states? So those are the equations. They were first written down by Lotka in 1921. So now we're going to ask, well, what are the steady states for these equations? So A dot equals B dot equals 0. That gives us the steady states. And so what we see then is that A into PB minus D is equal to 0. And that will be, if that steady state would imply that either A is equal to 0 or B star is equal to D over P. So that's one steady state. And then the B dot equals 0 implies that B into B minus PA is equal to 0. And so that means that either B star is equal to 0 or A star is equal to B over P. So that's the so those are the possible steady states. So we can write that down in the following way. The steady states are A star, B star, either equals 0 and 0, or A star, B star equals B over P, D over P, like that. So those are the steady states. Now, a long time, what's going to happen? If A star is equal to 0, then what will happen is that B will go to infinity exponentially, and so that's not a steady state. So the only steady states are the ones that we have here. So those are steady states. They're not particularly interesting. But now let's go and have a look at their linear stability. So just as we talked about in the previous weeks, we can look at the linear stability. And so what we do is we say A is equal to A star plus some delta A e to the omega t. B is equal to B star plus delta B e to the omega t. And then what you find, so then you just plug in, and I'm not going to do the algebra. So you find that 0, 0 is unstable. 0, infinity is unstable. And if I look at the fixed point B over P and D over P, that fixed point, if I linearize around that, what I find is that omega is plus or minus I omega 0, and this number omega 0 is the square root of B times D. So that's the behavior. So it's a marginal mode. It's not unstable and it's not stable. So the interpretation of that is that if I were to draw my phase space, so here is B, and here is A, here is 0. So then what I have is a fixed point. Let's say this is the non-trivial fixed point over here. And then what we've discovered is that there are, let's use a different color, there are orbits then that go around this fixed point, like so, and so these represent oscillations, and this is known as a center, because there's a center where there's no oscillations, and then as I go out from the center, then I have a periodic behavior, and which orbit you're on, the orbits that the orbit depends on the initial conditions. So if you say, well, at time t equals 0, I'm over here, then that tells you that you are on this particular orbit, and then off you go on that particular orbit. Okay, so if that statement were true, what you should be saying then is, well, that's a bit strange. If it's determined by the initial conditions, then that means that there must be a conservation law. So in fact, these equations, which are nonlinear, actually do have a conservation law. So if this were true, then there must be a conserved conservation law. So let's go and find it. So I'm going to go and show you a very simple way to construct the conservation law. In the notes, I don't know if I'm going to do this in great detail right today, but if you look in the notes, I show you two other ways to do it, and showing you how you can turn these equations into Hamilton's equations. So in disguise, this is actually a Hamiltonian system. So here is the quick way to do it. This is what you would notice if you just look at it. So what you might say is, well, if I take the two equations, dA by dt and dB by dt, and divide them, then I get an equation for dA by dt. So that is A dot over B dot, and that is equal to PAB minus dA over PB minus PAB. And that I can write as A times PB minus D divided by B into B minus PA. Okay, so that's just high school algebra. So now let's then integrate those equations. So in this representation then, so we can then integrate. So if I take the integral from, say, 0 to t of dA over A times B minus PA, then that has to equal the integral from 0 to t of dB over B into PB minus D. Okay, and so I can do those integrals. And so what I then get is that B times the logarithm of A of t minus P A of t minus B log A of 0 equals same thing with B, or something similar with B. P, let me get it right, P B of t minus D log B of t plus D log B of 0 minus P B 0. And so that means that B log A of t plus D log B of t minus P A of t plus B of t is equal to B log A of 0 plus D log B of 0 minus P A of 0 plus B of 0. Okay, so that's the result. And so you can see that because this is true, then what this tells you is that there's a conserved quantity which is C of t is equal to B log A of t plus D log B of t minus P A of t plus B of t. Okay, and that's fantastic. So we have it's like a harmonic oscillator. We have a conserved quantity. We have periodic oscillations. There's a beautiful theory for it, and you can do this. You can extend this and show that this is that there is a Hamiltonian formulation of these equations, and you can even write down Liouville's theorem. So that's all beautiful, but it's completely wrong. Okay, and why is it wrong? This is wrong because this is not structurally stable. Well, structural stability is something that is very related to renormalization group theory. And I'm not going to go into that relation, but I'm just going to show you that it's not structurally stable. So what structural stability means is the following idea. If I have a model of a physical system, let's call it M, and that model gives you physical predictions that we could call P. And then you might say, okay, well, that model of the system might not be completely correct. I might have, say, the viscosity in, say, a description of fluid mechanics, but I might be missing higher order terms like hyperviscosity and slight compressibility, other things like that. It's an approximation. So you might say, well, okay, in reality, that model might not be quite right. So I could, in a principled way, improve that model. And as I improve that model, then I'm going to make a change in the predictions delta P. So this over here is model, and this over here is predictions. Now, when we do physics at all, what we expect is that if delta M is of order epsilon, then we expect delta P to also be of order epsilon. I make a small change to the model, I'll make a correspondingly small change to the predictions, and that's fine. If that weren't true, we wouldn't be able to do physics in the first place. So if that's true, that's called structural stability. So if, on the other hand, if delta M is of order epsilon, but delta P is of order 1, then it's not structurally stable. And that causes a problem. If that's true, then it basically means that physics / science is hard to do in a principled way. I'm not going to go into details about that, but it's a very basic principle of science. Okay, so let's now take a look at these equations, and now let's ask what happens when we add a finite carrying capacity. So our goal here is the following. I'm going to assume that there is a fixed resource of food available to the prey. So basically, in terms of our sort of conceptual model, that just means that the prey live in a field, and the field has a certain size, and it has a certain amount of grass in it, or whatever it is that the sheep eat. So there's a fixed resource available, And that's physical, because when we look at what we had over here, remember over here on the left-hand side, we had a fixed point which grew exponentially in time. Where did I say it? Somewhere here. Yes, this thing over here. So for A is equal to 0, the prey population increases exponentially, and so this is the thing that is unphysical, because that can never happen. Eventually, there'll be a limit to growth. So let's put in the fixed resource of prey, and see what that does. So the way we do that is, let me skip the my side notes. So we put in a carrying capacity. That's what ecologists call it. And what that does is basically giving you what's called logistic growth. Okay, so those are the buzzwords. So let's see what it actually means. So what we do is we modify the B dot equation. So here is what we had before. Now what I'm going to do is I'm going to add another term. So I'm going to add a term here, which goes like this: 1 minus B over kappa. Okay, so the point about this is that kappa is the carrying capacity. And the idea is that when B equals the carrying capacity, then the growth rate stops. So it basically means that the prey growth cannot go unbounded. So this here, this thing here, that's carrying capacity. And then what this term does, this means that this whole term here then means that growth stops when you run out of resources. Okay, so that's a perfectly good model. The A equation stays the same. So the A equation is the same. So now let's see what happens then to our analysis. A dot is equal to PAB minus DA, the death rate of the predators. So now what we do is we look for the fixed points as usual. So what we have, first of all, is A star equals B star equals 0. So that's total extinction. We have A star equals 0 and B star equals kappa. That is a boring but steady state. So we don't care about that. But there is a coexistence fixed point. A star equals 1 minus D over kappa P times B over P, and B star equals D over P. And this is what we're looking for. This describes coexistence of predator and prey. Okay, so that's the one we're interested in. So now what we have to do is say, okay, well, now we've got the fixed points. Now let's have a look at the linear stability. So now we examine the stability. And so what you find is that extinction is unstable. Put things in the ecosystem, it can then grow. The prey saturation is stable, but it's only stable if P is less than some critical value of the predation rate, which is D over kappa. And then there's the coexistence fixed point, and its stability is much more interesting. So if for P greater than PC, it is linearly stable. And the growth rate is this: omega equals minus dB over 2 kappa P into 1 plus or minus the square root of 1 minus 4 kappa P over B into kappa P over D minus 1. Okay, so if you felt so moved, you could just go and do this, so to do this calculation. But the main thing I want to point out is that there is a real part of omega. So let me write it like this: the real part of omega is negative, and that means that you have something that is linearly stable. And so if I look at the dynamical behavior, so now I look at my phase portrait. This is called a phase portrait. I didn't say that. So if I look at the phase portrait, so here again is A, here is B. So now what I have is some fixed point. But now what happens is that it's stable. And so the trajectories sort of do something like this. They just sort of spiral into this fixed point. And this is true for any arbitrary kappa. So this is true for arbitrary kappa. And that's why we know this is structurally unstable. These centers, these cycles that look like, that I told you are centers, they immediately go away when there's an infinitesimal amount of kappa. Okay, so now we need to figure out what's gone wrong. So the conclusion of this analysis: there are no persistent population cycles and even though we had a story, a bedtime story, that just keeps on going in a very boring, cyclical, predictable way, when you mathematize it in the obvious way, it gives you something completely different from what is your mental picture of the system. So there is no persistent population cycles in contrast to the intuition that motivated the equations. So this is structurally unstable. Okay, so the next question we want to ask is, well, what went wrong and how do we fix it? So the answer depends on whether you're a theoretical physicist or an ecologist. So let's talk about the ecology version of how to fix this. So the ecologist would say, well, this model is not very realistic. Okay, so in what sense is it not realistic? Well, remember that we use the law of mass action. We said that in order for a predation thing to occur, a predator has to be there, a prey has to be there. The probability of that happening is proportional to the product of the densities. This is just like the same physics that we use to write down, say, the van der Waals theory of gases and things like this. It's the same law of mass action approximation. So the model does indeed lack realism. If you interpret this as the predator has to go out and then what is the probability of a predation event? Well, here's the predator. Then it has to sort of hunt around, find the prey, grab the prey, catch it, and then eat it, and whatever it does. There's a whole bunch of processing that has been ignored in the model. So that lacks some realism. And one of the consequences of that picture is this. Let's suppose I have so many prey in the ecosystem that the predator is just going around, and it doesn't have to wait for prey to come there and then be able to catch it and eat it and so on. It just grabs it and eats it, grabs it and eats it, like that. So if that's true, if there's so many prey, then the predation probability should not be limited by the density of prey. It will only be limited by the number of predators around. So the model lacks realism. And in particular, the realism that it lacks is, for example, how do predators catch and eat the prey? That's one of the things that you might want to model. And in particular, I'm going to sort of simplify the argument that they use, but basically at high prey density, it is not a rate limiting step to catch a prey. So then what you say is then, okay, well, so that means if it's not a rate limiting step, then that means as b goes to infinity, what that means is the predation term should be independent of b. And so the way we can model that is we say, well, fine. So then what that predation term was just PAB. That's a low density approximation. So at high densities, we want it to be independent of prey. So we're going to replace that by PAB over some constant plus B. So this is just some constant. And then what's going to happen is as b goes to infinity, then the b is going to cancel out. So what that means is that for b much less than whatever this constant is, we still have the PAB as we expect, but for b much larger than whatever this constant is, this PAB term now becomes independent of b. And so that's the basic idea. So then if I write down the differential equation, so then it looks like this, A dot is equal to PAB over C plus B minus DA, and B dot equals B into 1 minus B over kappa minus PAB over C plus B. And this is really great. When you analyze this system, which I'm not going to go into details, this nonlinear system of equations can exhibit limit cycles. Okay, so what is a limit cycle? So the limit cycle, what that means, so I draw my phase portrait. So before, what we had was some sort of fixed point, and everything scaled, everything spiraled into that fixed point. So now what actually happens is you do have a cycle. So let me draw the cycle sort of something like this. But this, imagine that this is not the fixed point. This is now the initial condition. An initial condition. then what happens is the trajectory of the system sort of goes like this and eventually is attracted to this cycle. And if the initial condition were over here, another initial condition, then what it would do is it would sort of spiral in towards this thing. So the limit cycle is a long time attractor of the system. That's independent of the initial conditions. Okay, so that's not a bad solution. Okay, so it's not like terribly stupid or anything like this, but it's not correct. Okay, and how do I know that it's not correct? So it's not correct or not satisfactory. I mean, you can decide what you mean by correct. It's not satisfactory for the following reason. That it introduced a new physics. I'm saying physics, but what I mean is new physics, or if you like, biological realism. And this whole assumption here, what I on the left hand side, what all of this is known as, this is known as type 2 Hollings functional response, telling you how the predators respond to the prey in a very detailed way, and you can make more mechanistic models of that as well. So we introduced a higher level of biological realism. But now I'm going to tell you that even if you don't do that, you can still recover population cycles. The difference is that in this case, the reason that you don't get population cycles is because of the approximations that we made, not because the physics that was included in the model was wrong. So we had our bedtime story of the population cycles going on forever, sending you to sleep. And then we did the calculation. That didn't work. So we said, well, we put in the wrong physics. But in fact, if you simulate that whole process, you do get population cycles, and we don't need any extra physics. So it's not satisfactory for the reason that it introduced new physics. And how do we know this? So if you do a simulation of individuals in an ecosystem obeying the following rules, I'll say that what they are in a minute, you do get population cycles. With no new physics. So in other words, my claim is so in other words, the claim is that the problem is in the calculation and not the description, not the physics that's included. Okay, so let me tell you about how we do that, and let me go back to the to our basic model here. So let's go back to this model. Let's go back to this one. So let's go back to the Lotka-Volterra's equations. So again, I'll just write them here just to make it easy to read. So that's how we are describing the system. But in reality, you have a system like this. Well, in fact, I drew it over here, didn't I? Why am I drawing it again? Okay. Why am I drawing it again? Let's get rid of that. Okay, so what's happening is these things are moving around. And so we can think then of individuals of A executing the following motion. Whenever they move around, whenever they run into B, a stochastic event happens with some probability P. The predator eats the prey and then uses the energy that is there to make a baby predator. And then we can also have that the A with some probability dies and goes to 0. And then we also have the fact that B will eat the food with some rate B and then produce baby bees. So the difference between this over here is that here in this description on the right here, these are integer variables. They're not densities. So this tells you the number of predators. So basically the number of preys. So when a predator meets a prey, the number of predators goes up by 1, the number of prey go down by 1. That's what's happening in the top reaction, and so on and so forth. So these are integers, so the changes in A and the changes in B are plus or minus 1. Okay? Whereas over here, everything is a continuum. And the changes are just, small numbers. So once you have that, then you have to ask, well, and then we're going to allow these things to diffuse around. So now you can ask, well, what happens if you simulate this? So if we now simulate the individual level model, so we're going to call the individual level model. So that's the individual level. This is at the left-hand side at the continuum level. If you simulate the individual level model using Gillespie algorithm, I'm not going to go through how you do it. What you find is that you get perfectly good, persistent population oscillations. And this individual level model, I've only shown you these equations. If this is true if I add the carrying capacity as well. So you might ask yourself, how do you add the carrying capacity? Well, the carrying capacity means that there's a constant, you can only support a certain number of individuals in the ecosystem. So what that means is if there's only a certain amount of food, then the prey, the sheep, are competing for the grass. So they're fighting each other. So what's actually happening is the prey are competing, and I can write down a competition term, which is something like that, prey competition. So B plus B with some probability goes to B, and that this term, if I add that to the individual level model, that reproduces the carrying capacity. So now we know that if I don't have any other physics other than carrying capacity, populations being born and death, predation, that without any assumptions about functional response definitely gives me persistent population cycles. And now we need to understand why it went wrong when we did it in differential equations. So
if I do the simulation with like a lot of A's and B's, like does it reproduce the just like behavior?
I'm going to show you. I'm going to show you now how to write down a mathematical model of the individual level description. Okay, and I'm going to show you that if I then take the mean field theory of that, like you're saying, the large number, the mean field equations are the equations I've already shown you, the Lotka-Volterra equations. Okay, but and of course it won't predict oscillation cycles. But what I'm going to show you is that the lowest order corrections in 1 over the square root of n does give you the oscillations. So if you have an infinite number of population, then the average of those equations will just say that the population, you don't see any cycles, because if I average over many of them, they'll all just average out to give you a constant. But in any realization of the system, you see population cycles. And those are driven by the stochasticity. So in this case, and in the Turing patterns that I'll talk about next time, the reason that you get patterns is because the patterns are stabilized by noise. Normally you think of noise as destroying something. In these problems, noise actually stabilizes the patterns. It's very amazing. Okay.
Another question. So if I was like trying to look up cycles in this, like have people tried looking at like some time delays in the system?
Yes, of course. Of course, you could. There's a million things you can do, but for us as theoretical physicists, the point is this: with just the physics that was originally put into these equations by the ecologists, and you mathematize that, it doesn't, in the way I just showed you, it doesn't give you cycles. If you mathematize it correctly, using techniques that are the topic of this class, then you do get cycles. So yes, anytime you take an equation, you say, I want to make it periodic, the easiest thing to do is put in a delay. Yes, of course, you can always get any answer you like, but that hasn't solved the problem. And moreover, it's testable. Okay, so you can test. I'll show you at the end. I hope I get to it. If I don't, I'll do it next time. We have enough lectures to do this. I'll show you that we can make a prediction that you can test this in real data. Okay, so the stochastic theory and say putting in a limit cycle, putting in a delay, and so on, those make different predictions for the power spectrum of the system, and you can test those experimentally. So the correlations that you get in space and time from looking at the stochastic mechanism are different from what you would get if you just try to fake it by deterministic equations. I want to go on, okay? Okay, you can ask me because I'll probably going to answer your question, okay? But from the point of view, an ecologist might say, well, why do I need this fancy math? Well, actually, the answer is when you describe more complicated problems, like for example, ones where you have evolution along with the ecology. Okay, so again, you can work the theory of that out, which I did like 10 years ago, and again, it's not a trivial calculation, but you can do it, and you show that when you have evolution in the problem, then what happens is that the phase lag between the predator and prey goes from being pi by 2, which is what I've already shown you, to pi, and you can predict that, and you can predict all sorts of things like that, and it mimics what you see in real experiments. So you don't have to put in the answer. You can calculate the emergent phenomena, which is the whole point of this course. So let's go and see how to do this. So let's make a couple of comments. So comment number 1 is you can see that the continuum description must break down. When Sridhar was asking his question, you were thinking in the right way. You were thinking, well, it's a mean field theory, it should be a large n limit of some model. So, do you get that in that limit? And the answer is yes, you do. So then you can ask, well, where is that large n limit going to fail? And the answer is it's going to fail where you're near extinction. So think about the system when it's near extinction. So it obviously breaks down near extinction. Why is that? Well, let's suppose let's take it a ridiculously small number. I've got 3 prey left in the system. Okay, then one of them gets eaten, down to 2. Then that one gets eaten or dies, down to 1. Then that one gets eaten, down to 0. At that point, the whole dynamic stops. Okay, the ecosystem is no longer, you no longer have coexistence. But the differential equation doesn't know that. The differential equation is looking at densities. So it's just looking at some A and B, which has just some functions, and it will keep on going, even though the actual system with integer numbers of particles, once everything's gone to 0, everything dies out, but the continuum description will keep on going. So near extinction. So when the prey go extinct, then the predators will go extinct as well, and everything stops. And but in the continuum description, that keeps going. And that is definitely bad. So you already know that that description is not, it may be accurate asymptotically in some limit, although even then it's not quite correct, but you can see that it obviously is limited, and we want to find out how do we understand all this properly. So let me, it'd be great if I had a quick way to add, well, I'll just do it like this, add page. Let me do it again. Okay. All right, so let's go on. So the conclusion of what I just told you is that the discreteness of individuals is actually important. Another way of talking about discreteness is to say that they are quantized. Okay, so let's now try to mathematize this. And I'm not going to use the most sophisticated formalism today, but it's still tricky. But so let's do it in the following way. I'm going to now look at how do we mathematize this. So we're going to mathematize using what's called the chemical master equation, sometimes master equation for short. There's a quantum one too, by the way. We're going to mathematize using the chemical master equation. So we're going to mathematize it, and then we're going to look at the n goes to infinity limit. And what we will end up deriving is we will derive the Lotka-Volterra equations as a mean field limit. And we'll see that the oscillations, the population cycles, arise from fluctuation corrections to mean field theory, and they are amplified. I'm not going to spend a lot of time on the amplification, and they're amplified, and that they make observational predictions. And just to give you advance notice, so the field data on population cycles and ecology is really not that great. People don't have very long time series. But so what we did is we worked out the extension of this to spatially extended systems. So we worked out the theory of stochastic Turing patterns. And then we actually did experiments using synthetic biology to look at signaling molecules in biofilms where the discreteness is not sheep and wolves, but is different signaling molecules in a biofilm. And we were able to then use fluorescence spectroscopy to measure those and then verify the predictions for the correlations and so on. So let me go through how we do this. So we're going to, so that's our goal. So what are we actually going to do? So we're going to write down the probability distribution of the system when it has different states, and the states are specified by the integer populations of A and B. So let's write down all the processes. We're going to assume that the system is well mixed. And well mixed just means that somebody's come in and just stirred everything up, so there's a uniform density in the system, so we ignore space. And so that's our picture. So then we have the various processes. So we have A goes to the empty state with probability dA. We can have prey going to 0 with death rate B. So that's just death processes. Then we can have predation. So we have predation, we have A plus B goes with probability P per unit volume into A plus A. So that's predation. Then we have prey reproduction. So B goes with some rate B per unit volume to B plus B. That's prey reproduction. And then we have prey carrying capacity. So B plus B with some rate C over V goes to B. That's prey competition for limited resources. And so what we do is we write down an equation for the probability of the system being in a state. So we're going to write down P of L and T is our main object. So this is probability. This is the state of the system. And T is time. And so the equation that describes this is dP of L and T is equal to the following. So what can happen is I'm in a state L, so then I can make a transition to another state L prime with some rate. And if I'm in a state L, I can make a transition out of that state into another state with some other rate. So basically I have transitions into the state and I have transitions out of it. So what we're going to model then are transitions into the state L, and we're going to model transitions out of the state L. Okay, so let's go and write those down. So the transitions into the state L go like this. I start off with some state L prime time t, and then I make some transition with some rate L L prime. And then I sum over all possible states L prime. And this T is the transition rate from state L to state, so from state L prime to state L. So that's the first term. And then the second term is that I start off in state L. I transition into state L prime until I have another matrix TL prime L that starts off with P of L. So think about it this way. If I'm going to go, the rate at which I change the probability in state L is, first of all, what is the probability of being in the state L prime, where L prime is different from L? And then what is the rate that I transition into the state L? And then what if I'm given that I'm in the state L already, what is the probability that I transition out of it? So in these things over here, this L prime is not equal to L, and this L prime is not equal to L. So this is transitions into the state, and then these are transitions out of the state L. Okay, so this matrix here. So this is the transition rate from L prime to L. That's what this thing means, and we can calculate this using the occupation numbers of the states. So A and B will have occupation numbers, which I'll call, with great imagination, NA and NB. So now what you want to enumerate in order to calculate that thing. I'm not going to go through it in detail. It's relatively straightforward, but you have to think about it carefully. So what you have to do is enumerate the ways to attain the state NA, NB. That would be what we mean by L at time t. From earlier states. And those earlier states might be, for example, the state where you have the same number of predators, but the number of prey is down by -1, etc. So so to get to NA and B from this state, you would need to do, in this case, a prey birth process. And then you just do this for all of them. So I can write down what those transition matrices are, and so I'm going to just write them down. And I'm not going to work through how I got that, but if you're interested, it's not that hard to go ahead and do that. So let me write them down. So I think I've got all of them here. I'm just going to write them down. They'll be self-explanatory. So I start off with the state NA -1. Well, I want to access the state. I can get there from NA NB, and the rate for that is going to be that one of the A's dies. So that goes like this, and then I get that T NA NB -1 NA NB, that is equal to DB NB plus C over V NB times NB -1. T of NA plus 1, NB minus 1, NA, NB, that is equal to P over V, NA, NB, and T NA, NB plus 1 from NA, NB, that is equal to B, NB. So that's how I can write down these transition matrices. And you can see already how it is that I keep saying you could use quantum mechanics for this, because I could write down a step operator which I'll write as like this, EI plus or minus acting on some function of the NAs and NBs. When I do that, what that does is it acts on the variable NI and adds or subtracts 1. So I can write down these step operators, and you're probably mentally thinking these are like annihilation and creation operators if I were to define the system in a Fock space, and I can be equal to either A or B, and so you can then work out the theory like that. Okay. So that's technically what you do. So let me show you one way that you can treat this. So what we're actually interested in, we're interested in the deterministic limit. And what we really want to do ultimately is we're going to see that the deterministic limit just gets us back to the Lotka-Voltaire equation that we've already seen. So we're going to go and look beyond that. So we're going to try to look in the limit where the noise is weak. So just like Srijit was asking, if I have a large, huge, asymptotically large population, you might expect mean field theory to be valid. And so then you want to look at what are the lowest order fluctuations around that. So in other words, we want to look at the weak noise limit. So you might say, well, so we're interested in the deterministic limit. So that suggests doing a kind of weak noise calculation. Well, the noise comes from the changes in the integers that describe the actual state of the system. And so what that suggests is, well, why don't we just write it like this? If I've got f of n plus n plus 1 minus f of n, we can approximate that as being df by dn. So that's true as long as n is much larger than 1. So then what we're going to, so that suggests then that I can take my ladder operators, my step operators, and I can write that down as a Taylor expansion that looks like this. So I can just do a Taylor expansion like that. And then what I do is I substitute this into the chemical master equation. So I'll just call it the master equation. And then what you end up with is an equation called the Fokker-Planck equation. And that equation looks like this. I'm going to just write it down just so that you can see it. I derived a functional form of this in the previous lectures. I didn't go through it in detail, but I derived it nonetheless. And it's also derived in my book, as a matter of fact. And I derived it there from Langevin equations, but here we're doing it in a different way. And so the equation you end up with is something like this. So this is a linear equation for the probability density of the system. And this AI and BI, those are respectively a vector and a matrix. So this I'm not going to write down what these things are, because actually this expansion is not the one that we're going to use. But this Fokker-Planck equation corresponds to a Langevin equation. We talked about Langevin equations in the previous lectures. So in this Langevin equation, n is now a vector, which is equal to just NA and NB. This is some matrix, which I'm not going to write out what it is. And then this is a noise, which is correlated eta I of t, eta j of t prime equals the matrix Bij delta of t minus t prime. And this is one way to make an expansion of the master equation in this limit. Now, the problem with this, this equation really doesn't properly describe the system except for very large n. Larger n than we want to do. This equation will not, if you do it systematically, will not give you, well, is not a systematic expansion. So this is a closure, not a systematic expansion. Because the approximations aren't justifiable. Where it breaks down, remember that we saw earlier, we argued that the continuum approximation is going to be least good when you're near extinction. And that's not valid for this. So next time, we're going to finish here. So next time, I'm going to show you a different expansion that we can use, which is like the 1 over n expansion in quantum field theory, called Van Kamper's expansion. I'm going to show you how we can then perform that and then describe what's happening in the system. Okay, so that's it for today's lecture. So let me turn off the recording.